So we're going to talk about what a limit of a function is. So we're going to start with an example. We're going to use this function f of x equals x squared plus 3x minus 2. We want to find the limit of f of x as x goes to 2. But before we start doing that, I just want to mention a limit is just where does the function values head as x heads to some number. So in other words, what we want to know here is what y values are we getting from this as x is heading towards 2. Sometimes it's fairly easy to find, sometimes it's a little work. We're going to actually do this what we call numerically. So we're going to find this answer by going through and trying to find out what the value is, what we call numerically. And so what that means is we're going to pick values to get closer and closer and closer to the number 2. We're going to pick values for x that get closer and closer and closer to 2, and then we'll see what happens to the function values, what happens to the y values. All right, so we're going to pick a number like 1's pretty close to 2, and so all I'm going to do is take my calculator out and do 1 squared plus 3 times 1, which is 4, minus 2 is 2. So actually I don't need a calculator for that one. And 1's maybe not as close as we could get. 1.5 might be closer to 2. So again, I'd plug the 1.5 into my function. 1.5 squared plus 3 times 1.5 minus 2. And I'd see what I get. And when I put that in, and this time I did use a calculator, I get 4.75. So one thing I notice right now is these numbers don't seem to be going towards anything in particular. We went from 2 to 4 point something. So, but we still aren't very close to 2. Let's see if we can get closer. Maybe letting x be 1.99. That gets us a bit closer to 2. Again, I'd put it in my calculator and find out what a value I get. When I do that, I get 7.31. And then I'm going to say, well, now I notice I'm going from 2 to 4 to 7. Still don't look like I'm heading to anything. But 1.9 isn't all that close to 2 either. Can I get closer? Well, yeah, I can go to maybe 1.99. That's a bit closer. And when I plug that into my calculator, I find out that that's 7.99301. And so now I notice I went from 2 to 4, that wasn't getting close to anything, and then 4 to 7. But now we're going from 7.3 to 7.9. Now I notice that my y values, my whole number here, is basically the same number. These two aren't very concrete of what they are, but these two now are the same number. So I wonder if I could get even closer. So maybe 1.999 is even closer to 2. I mean, that's pretty close to 2. And when I plug that in my calculator, I get 7.99301. So now I notice I went from 2 to 4 to 7.3 to 7.9, and now 7.99. So now I notice, hey, these seem to be getting the same numbers. So it looks like we're doing pretty good. But now my question is, was there any reason why I started at 1? I mean, 1 is close to 2, but why couldn't I start somewhere else like 3? So let's make another table of values and function values. And so instead of starting at 1 below 2, maybe I could start at 3 above 2. And when I did that, I got 16. Not great. Doesn't show me anything. I don't see a trend yet. 2.5 is a bit closer to 2. When I did that, I get 11.75. Getting a little bit, I still don't see a trend. So I gotta go even closer. Maybe I'll do 2.1. That's a bit closer to 2. When I do that, I get 8.71. Again, I'm not really seeing a great trend, but I am noticing I'm getting smaller. Went from 16 to 11 to 8, so I'm getting smaller. But again, 2.1 isn't very close. Let's try 2.01. That's a bit closer. And then I get 8.0701. So now I see a kind of trend going. Went from 16 to 11 to 8 to 8 again. So I now start seeing a trend. So let's get even a little bit closer. 2.001 is even closer to 2. And that time I get 8.007001. So now it looks like I'm going from 16 to 11 to 8 to 8 to 8. I'm getting even closer to 8. And remember, from this side, I went from 2 to 4 to 7 to 7.9 to 7.99. So it looks like I'm heading towards 8. So it looks like the limit, and the way we write this is LIM as x goes to 2 of my function appears to be, so it's approximately equal to 8. And there's what I have. Pretty cool? All right, so we have that information we could do. What I could also do is I could have done it graphically. So I could have also done a graphical method for this instead of a numerical. And what I would do in that case is I'd do a graph. So first I'm going to create a graph. So I'm going to go in. I like to use Desmos, so I'm going to go into Desmos. And I'm going to go ahead and type in my function. Remember, my function was y equals x squared plus 3x minus 2. The thing is that my graph, it doesn't show me a whole lot here because I see 2, but I don't see the 2 on the graph. So I'm going to go change this a bit. I don't need to change my x's because I want to head towards 2, but I'm going to go ahead and change my y's. I'll start at the bottom here, but maybe instead of going at 5, let's go up to 10 and see what we can see. So now I have this graph. I'm going to go ahead and take this graph and snip it and bring it into my function. I'm going to go ahead and put that into my notes. Oops. All right, so here's my graph. And again, I want to see kind of where am I heading? Where am I going with this? So that's now what I want to look at is where am I heading as I head closer and closer and closer to 2. So again, what we're doing is we're letting x get closer to 2 from either direction. I want to see where y goes. So from here, when we're at 1, we can see we had, whoops, some number up there. And then if we came from the other side at 3, whoops, just not a very good drawer here. If we come from 3, we can see kind of where we're going. And then we're going to keep doing that. We're going to get closer and closer and closer in from both sides. Graphically, what we're doing as we're heading in and what's happening. So if we notice, what we're doing is we're getting closer and closer and closer in on the function value. And it looks like as we're moving in from this way on 2, we're heading this way, top and bottom, towards 8. So we can also see the same thing, is we can see that graphically we look like we're heading to 3, to 8 also. So the limit as x goes to 2 of my function looks like it's about 8. This isn't perfect because and that's why I have approximately equal to, because I don't know for sure that it's 8. There might be something weird that happens really close to 8. But we're going to say it's probably 8. So now let's define kind of what a limit is. So I'm going to give you the definition of what a limit is. The limit as x approaches some number, we'll call it a, of your function, is some number we'll call L. And what this means is you can make f of x, your function, arbitrarily close to L by taking x sufficiently close to a, but not actually equaling a. The function doesn't have to exist at a. It just means we're getting closer and closer and closer to it. So that's kind of the definition of what we're talking about and what is happening with this. So when we say arbitrarily close, that's kind of it's really how close you want to get. Sufficiently close, it's really, how close can you make x to your number? Graphically, what this means is if I have some function here, Let's say I have some function that's doing this. And here's a. And all this means is that we're going to let a get closer and closer, x get closer and closer and closer to a. And when we do that, again, we're going to come up, we're going to see over here, we're going to come up, we're going to go over here. We notice that we're getting closer and closer and closer in on some value here. And that value is L. So that's kind of what this is all about, is what it's doing. Again, it doesn't have to be at A. So as another example, if I were to draw another graph, I could have a graph that does this, and then has a hole. So here's my A. So here I can come in towards A on both sides and head towards some value. And I'm heading towards that value L, even though the function doesn't exist at L. It has no function value there. I still can talk about it and what it's doing. So I can actually still have something going on, even the function doesn't exist there. I can still work on getting closer and closer and closer in on that value. And again, what you're doing is you're letting x get closer and closer and closer towards A each time. And even though at A it doesn't exist, you actually are getting closer and closer and closer to what that hole is. So you can find out what value that is. And we call that L. So let's try another example. Let's try to find the limit as x goes to -2 of x plus 2 over x squared minus 4. Oops, I seem to have the answer there already. Let's take that answer out. Okay, so we're going to go ahead and do this. You saw what the answer is, but let's actually show you how we can do this. We're going to do it numerically. Graphically is nice to have a visualization, and sometimes it's useful to visualize, but sometimes it's not all that great to find out what the value is. So numerically is really good. So we're going to have an x value, and then we're going to have x plus 2 over x squared minus 4. So we're going to let x go to -2. And I want to mention, by the way, that as x goes to -2, if we actually just let x equal -2, you'd have -2 squared, which is 4 minus 4, you get 0 on the bottom. We can't have 0 on the bottom, so that would be a problem. So we can't actually find this just by sticking it in as you think you can. You can't do that because the function actually doesn't exist at this point. And I also want to mention that if I plug -2 in the top, I get -2 plus 2, which is 0. So I get 0 over 0. And believe it or not, that's not 1. That's not 0. It's what we call undetermined. We don't know what it is equal to. And so we're going to numerically go find out what it is. Okay. So we're letting x get closer and closer to -2. Let's start with -1. And when I plug -1 in, I get 0.333 polyrepeating. All right. But again, -1's not that close to 2. Let's go to maybe -1.5. That's closer. When I plug that in, I get 0.2857. Again, that's still not really close. So we're going to go -1.9. I get -0.2564. And now I'm noticing, looking for trends is what you're doing here. You're trying to see, is there a trend of these values? So I'm noticing the first decimal place seems to be fairly close to being consistent, but I still don't really know what it's doing. So let's get a little bit closer. Let's do 1.99. That's a bit closer. And I get -0.2506. So now I notice, hey, trend-wise, it looks like we're getting closer to -2.5. Maybe we can go just a little bit closer. -1.999. When I do that one, I get -0.25006. So that's looking pretty promising, like we are actually heading towards, we're trending towards a certain value. And this is the idea of limits, is you're letting x do something, getting closer and closer and closer to a value. So you're letting it get as arbitrarily close as you can, or sufficiently close, I should say. And you're noticing you're letting this is going towards some number. Now, we probably should go to the other side too. What I mean by the other side is we picked values that were less than 2. There's no reason we had to do that, or less than -2. There's no reason we need to do that. We could have picked numbers. Actually, I'm sorry, these were bigger than -2. We're picking numbers bigger than -2. There's no reason we couldn't have picked numbers that were smaller than -2, like -3. When I did that, I get -0.2, -2.5. When I realize I'm going to change my color here. -2.5, I get -0.222, -2.1. I'm going to get -0.2439. So again, I'm looking for a trend. I notice it looks like we're heading to -0.22, but the second decimal place doesn't seem real confident yet. So let's get even closer, -2.01, -0.24937. So I'm still not real confident about that third decimal place. It'd be nice if we could get even closer. -2.001 is -0.2499375. So now it looks like, again, trending wise, we're heading towards -2.499, probably -2.5. So it looks like the limit as x goes to -2 of x plus 2 over x squared minus 4 looks like it's approximately -0.25. The reason I still say approximately the looks, you might sit there and say, hey, this looks really good, but in reality, it's not perfect yet. And we can't know for sure that it's exactly equal to this unless we do algebraic techniques, which we're not going to do today, or in this video, I should say. Another concept is kind of one that we've been doing. One's called a one-sided limit. Here we came from numbers that were bigger than -2. So -1 is bigger than -2. It's to the right of -2 because it's bigger than -2. All these numbers are bigger than -2, and we're heading towards them from the right. -3 and so forth, these are all numbers that are smaller than -2. They're all to the left of -2, so we're thinking they're coming from the left. So we can actually define now one-sided limits. The limit from the right, the symbol for this is the limit as x goes to a with a plus sign. Plus sign because to the right are positive numbers. So we put a little plus sign there to say we're to the right of my function. And the limit from the left of my function would be the x as a goes to from the left with the little minus sign up there. Again, minus signs, negative numbers are to the left, so we think of that as just a way to write it. All right, so we can now find these two limits. Notice in both of these examples we did numerically, it looked like we're heading towards the same number from both sides. All right, so in this case here, we were heading towards, looked like the same number from both sides. That doesn't always happen. So what I want to do is another example, have this one kind of do the same thing where we're kind of finding out where we're heading and see what happens. So this time, again, I'm going to do this numerically. So I'm going to pick x values, and I'm going to do 1 over x cubed. I'm heading towards 0, so I'm going to pick a number from the right. So 1 is bigger than 0, and it's to the right. Put 1 in there, of course, you get 1. Pick a number closer, like 0.5. And again, you're not just going straight to a number really close to 0. You need to get closer. You need to watch for trends. So you're just trending this towards 0 to see where these numbers are trending towards. So when I put 0.5 in there, I get 8. When I put in 0.1, which is even closer to 0, I get 1,000. When I put in 0.01, I get 1 times 10 to the 6th, even some bigger number. Let's go to even closer, 1.001, I get 1 times 10 to the 9th. So one of the things you may notice about this is these numbers are getting really, 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 really big. So you can think of these as these are heading towards infinity. Let's take numbers from the other side. So that's from the right. Let's do from the left. So from the left would be numbers smaller than 0, like -1. Put -1 in, of course, you get -1 back. get closer. Again, you're looking for trends. So you don't just jump straight to a number close to 0. You're looking for trends. You're going to let these numbers get closer. And you get -8. Negative 0.1 gives me -1,000. Negative 0.01, even closer, gets -1 times 10 to the 6th. And negative 0.0001 gets you -1 times 10 to the 9th. So one thing I noticed about these numbers is they're trending towards not positive infinity, because these are all positive numbers. This one's trending towards negative infinity. They're getting to be really, 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 really small negative numbers, or really, really big negative numbers. You want to think it that way. So one of the things I notice is that these aren't heading towards the same number. These are heading to positive infinity. This side is heading to negative infinity. So that might mean that they're not heading to the same place. They're going somewhere totally different. Graphically, what this looks like is if I go ahead and graph this in Desmos, and look at the graph of this. Again, this graph is x cubed. I'm sorry, 1 over x cubed. Whoops, what did I do? All right, let's try this again. 1 divided by x cubed. There we go. All right, so looking at this graph, and I'm not going to bring the graph into my Desmos, but looking at this graph, these numbers are going to go up. They're going to go heading up to positive infinity. These numbers look like they're heading down, and they look like they're heading down to negative infinity. So graphically it looks the same as what I'm seeing in my numbers. So graphically, again, I'll just sketch the graph here. This is what this function looks like. Something like this and something like this. So graphically, it gives me the same idea that these are never going to hit. They're never going to cross each other. They're never going to trend towards the same number. So that kind of tells me that this limit as x heads to 0 of 1 over x cubed does not exist. We use does not exist an awful lot. So we usually use DNE for does not exist. So that gets me back to this idea of when do these limits exist and what's happening with them. So let's go back and kind of fill in this definition of a limit. So the definition of a limit, we had the limit from the left and the limit from the right. Well, one of the things we notice is that the limit is only going to exist. It did with these other two. This limit was going towards the same number on both sides, and we knew that the limit was going to that. So the limit from the left must equal the limit from the right, and it equals some number. We'll call it L. So notice it's not infinity, though they can head to infinity, but that's not what we're looking at here. We're looking for where it's heading. So we've got some limit here. The limit would actually, the limit as x goes to a of their function would actually equal that limit. If and only if the limit from the left equals the limit from the right equals that L. If and only if is again a popular thing to write, so we write IFF for if and only if. What that means is if this is true, then this one's true, and if this one's true, then this one's true. And so that's what we have. Let's do one more example, one more graphical. So here's one more example. We're looking at, we're heading along here. We're heading towards some value here, heading towards some value. We want to see what's happening. So let's first look at the limit as x goes to 0. So as we're heading towards 0 from left and right, it looks like we're heading towards, I don't know, some number. We'll call it 3. It looks like it might be the number 3. So it looks like as we're heading towards the left and right towards 0, if I were to just look at my x values getting closer and closer to 0, my y values look like they're all heading towards 3. So we can say that this limit is 3. Now let's do the limit from the left and right as we're heading to 3. So here's 3, my x value of 3. I'm going to get closer and closer and closer from 3. Notice when I do that from the left, I'm going to head closer and closer and closer to these values, and my y values look like they're heading towards the number 4. So the limit from the left looks like it's the number 4. The limit from the right, as I'm heading closer and closer in, I'm coming up, hitting the graph, finding out what y value I'm heading towards. It looks like I'm heading towards the number 2. So again, the limit from the left and the limit from the right have to be the same number. They have to cross. You think of it as you're driving along this road and you're heading towards, you want to go to this road, but there's no connection between these. So we're heading towards here, we're heading towards here, and there's no way to get from here to here without jumping off a cliff or scaling a cliff. So this limit doesn't exist because we can't match them up. So we would actually say the limit D and A does not exist. It doesn't equal that, it does not exist. So we don't have an equal to. One last thing I want to mention is the limit doesn't exist, but at 3, the function value does. At 3, it looks like the function value is about 3. So it looks like at 3, the function actually does exist. It has a dot there. It has a number. It looks like it's the number 3. And that's the introduction to limits.